usual, I will give you a brief introduction on the lithium-sulfur batteries. And then, of course, we need to discuss the detail about the fundamentals. So what is the reaction mechanism of the lithium-sulfur batteries? And then, so as the most important part, so we will mainly focus on the cathode materials which are designed for lithium-sulfur batteries. So these cathode materials are mainly based on carbon nanomaterials. Sometimes polymer can be also used, and more recently, metal-based compound like metal sulfide, metal oxide, or metal nitride, they are also very attractive cathode material for lithium-sulfur batteries. And then in the end, I will give you a short summary about this part. As we already discussed on last Tuesday, energy density and capacity are two very important factors when we consider about the future possible application of the battery systems. And here, so here E is the energy density and C is the capacity. When we look into this plot here, so here's for this intercalation. So this is a classical cathode material for the lithium-ion batteries. And so I make example, for example, so NMC, so this is one of the most famous and most often used cathode material for lithium-ion batteries, which is based on the nickel magnesium cobalt oxide. And from this plot here, actually you can also calculate by yourself. So the theoretic capacity for this material is around 150, something like this. And then, so they have the potential window around 4. So you can use 4 multiply this potential window with this capacity. So you will get the theoretical energy density for MMC is around 630 watt-hour per kilogram. And as a comparison for the lithium sulfide, and we can also see from this process, lithium sulfide has a theoretical capacity more than 1,000. Although the potential window for lithium sulfide is a little bit small, so normally it's around 2 or 2.2, something like this. But due to its extremely high theoretical capacity value, so we can still get the theoretical energy density more than 2,000 here. So it's 2,500 watt-hour per kilogram. And another advantage for the sulfur, you can also compare the price. So for the typical NMC cathode, so it costs for 1 kilogram, so around 20 euro, and the price is still increasing due to the limitation of the cobalt in the world. However, for sulfur, so sulfur is often byproduct for the industry products. So the price for sulfur is really very low. So it's less than €1 per kilogram. So it's a huge difference. This is also the reason why researchers, I think, lithium sulfur will be one of the most promising candidates for the next generation battery system. Again, so I give you also comparison of sulfur with other electrode material. So for the graphite, so graphite is also a typical anode material for the lithium-ion batteries. And so it has a theoretical capacity more than 300. And the cost here, so you will compare the cost, you will see the sulfur is really one of the cheapest raw material we can use for the electrode. And also, if you compare with the theoretic capacity, so for sulfur, it's more than 1,600 milliampere hour per gram. And so this is now for the research which value we can achieve. So you can see already, so for graphite, due to the application of the lithium-ion battery is one of the most successful battery system available in the market. So that's why it's really nearly to the theoretical value. So you can imagine there's no space for the increase of the capacity for these lithium-ion batteries anymore in this case. And for the lithium copper oxide, so this is a cathode material for the lithium-ion batteries. Here you still have the space to increasing. However, compared to sulfur, you see you still have such large space for the increase of the capacity of the system. That's why if you look into literature, so the sulfur, so the paper on sulfur, it's every day you will get at least 2 or 5 papers published on this topic. So I just give you a short summary. So of course, so the advantage of lithium sulfur battery compared to that of commercial available lithium ion battery. So as we mentioned already, so sulfur is really cheap with high availability. So sulfur is one of the most so abundant element in the earth. And also for the lithium sulfur battery, you need relative charge time. So it means so you do not need to wait until the battery is fully charged. And of course, so in this case, you have very good eco stability for the lithium sulfur system. And also for the lithium sulfur battery, so they can operate at relative high temperature, so they are temperature stable. And compared to lithium ion battery, they are more safe. So you have a good security packed on this. And also, so you can even reach so the higher energy density by using lithium sulfur battery system. And so this Oxys, so this is one of the best company in the world. So this is company from UK, so in Cambridge. So this is one of the most, established company working on lithium sulfur battery. Actually, there are not so many company in the world have this technology to can have commercialized lithium sulfur battery. So Oxys is one of the best. So they are the leading player for the lithium sulfur battery market. And so they have also made a short summary compared to the commercial available lithium ion batteries. So here for the lithium sulfur battery, they have very good gravimetric density. And so this makes them very attractive for the application which you do not consider about volumetric density. So here I just want to mention to you, although lithium sulfur battery sounds very promising, but if you compare their volumetric energy density, actually they do not show much better volumetric energy density compared to that of lithium ion battery. And this is also makes them actually, lithium sulfur is not a promising candidate if you want to use as for the electric cars. Because I think when you have a car, you do not want to have your behind, it's only for the battery system. You want to have more space, put your stuff in your car. Instead have it's full of your battery system, to have the same energy density. So this is a disadvantage for lithium sulfur battery, considering the application in the electromobile. But on the other side, if you do not consider the volume of this battery system, so the lithium sulfur battery is very promising, for example, for these aerospace applications for flight, so for this new airplane, and also nowadays very famous for the airspace, so they use lithium sulfur battery, because in that case, you do not consider about the space, but you need to very low weight. So then they have a very huge advantage here. And again, so you can see they compare with the lithium ion battery, they have a higher safety issues and also the cycle life. So here, so the cycle life of the lithium sulfur battery, later we will mainly discuss on this problem. So it still need to be improved if we really want to have a good commercialized product. Because for the lithium ion battery, you can really cycle for more than 1,000 times, 1,000 cycles. But here, so the cycle life, because the Oxys, they give this best value. Actually, for our lab, work. So we are also working on lithium sulfur battery. So normally for lithium sulfur battery, you can normally work for the 100 cycles. And even if you want to increase the charge rate, so if you like shorten the charge time, you have even lower cycle life of this system. So this is one major problem actually for the lithium sulfur batteries. And on the other side, so you have better temperature tolerance. So you can operate even up to 80 degrees Celsius. And also, so the system is panicked if you think about your battery. So you have the sulfur, and later, so for sulfur, because it's not conductive, so it's an isolated material, so you need a host material. Normally it's carbon, so it's very beginning system, so it's also environmental friendly. So this is the main advantage for the lithium sulfur battery system. And also I give you so a kind of information. I hope you can keep this in your mind, because when we talk about the battery, the total material cost, of course, you have the cathode, anode, electrolyte, and you also need a thin layer film, so separator, and then you need also the housing and casing, or feed through system. So if you have the total cost of your battery, you will see, so the most of the cost here is based on the cathode. So that's why it will be very important to optimize the cathode system for the lithium sulfur batteries. Of course, so after we talk about the advantage, there are always remaining challenges for such kind of system. For the lithium sulfur battery, there are mainly 4 challenges for lithium sulfur battery. So on one side, because we use lithium as an anode, so during charge and discharge, so you will have the lithium dendrites growth in the system. And this lithium dendrites will lead to the short circuit failure in the battery system. So this is also one main challenge for the lithium sulfur battery system. And also we discussed already, so sulfur is a kind of isolating material. And if for the battery, of course, you need a good conductivity. That's why you always need to put or immobilize or embed sulfur into a kind of host material. In that case, of course, you reduce the sulfur content in your system, and this leads to the low capacity value of the battery. And also for the sulfur loading, so in the moment, the typical sulfur loading amount is around 2 micrometer per square centimeters. So this is square meter is the surface area about your battery. So when we talk about the coin cell, it's typical 1 square centimeter with a surface area. And you think about, so normally you have like 2 milligrams. So the amount of sulfur loaded in this battery is also quite low. So nowadays, there's also one very important topic is how to run the battery, so lithium sulfur battery, under extremely high mass loading of sulfur. And there's also paper discuss about this. So for the commercialization, it makes sense only when the sulfur loading is higher than 5 microgram per square centimeter. And the best system, of course, if you can reach 10. So this is the number you keep in mind. So, and also, so the polysulfide, so this we will talk when we talk about the mechanism, so the reaction during charge and discharge. One of the major problem for the lithium sulfur battery is the formation of the polysulfide during the charge and discharge. And the polysulfide is soluble in the electrolyte. So this leads to the polysulfide dissolution. And this, of course, will give a dramatic capacity fading during the battery charge and discharge. So these are the 4 main challenges we should solve for the lithium sulfur battery system. And of course, when there's a challenge, there's also possible methods to solve the problem. For the lithium dendrite growth, so nowadays, so the researchers, they are mainly focused on to do the pre-lithiation of anode or to protect the anode with a thin layer to prevent the growth of the lithium dendrites. And considering the isolating nature of sulfur, so you can using the conducting agent as a host material, normally it's carbon, so as the host material for sulfur. And for the low mass loading of sulfur in the cathode, so it's possible to use the high specific area carbon. So in that case, you can have the possibility to absorb more sulfur in your cathode. And in that case, to increase the mass loading. And of course, for the shuttle effect caused by the dissolution of polysulfide, so you need a kind of stabilizer agent, which can have either a physical or chemical confinement with the polysulfide. In that case, to prevent the dissolution of the polysulfides into the solution. And all these, of course, connect to the materials design. So it really needs the design of the electrode material for the improvement of the electrochemical performance of the lithium sulfur batteries. And before we go to the cathode system, I also want to introduce you the mechanism, so the fundamental of the lithium sulfur batteries. And so here is a typical coin cells. So this is 2032, so it's the size. So this is a typical coin cell type we used in our lab. And on the right side here, so this is like a plastic bag. So this is called pouch cell. And so normally in the lab, we are working with the coin cell type of battery cells. However, for the industry, they are more interested on the pouch cells, because here normally you have a much large area, so electrode material area, then of course you will with a higher energy density of your system. So this is directly related to the application of industry. And as the anode material, so this is lithium metal, so you have lithium as anode, and the cathode is sulfur, but you need a host material, so normally it's carbon, to improve the conductivity of the system. So you have cathode is sulfur in the host material. And in some cases, because you know carbon is kind of powder, sulfur is also kind of powder, how you can make a homogeneously cathode on it? Then you need to add the binder. So normally you need 5 to 10% weight percent of polymeric binder in your system. Then you can make a homogeneous slurry of the cathode, and then you cut it into, depends on the battery cell type you are working with. So then you will get your cathode material. For the electrolyte system, it's always, so this is the commercial, so also the most often used electrolyte system. So this is a mixture of DME with DOL. And so here you already see, so again, so you know for the different battery system, you need use different electrolyte. So just keep in mind. So for the lithium ion battery, we always use this carbonate-based electrolyte. But for the lithium sulfur battery, so normally you need use such kind of DOL or DME-based electrolyte. And of course, it's the same. So you need to add some salt, like lithium TFSI or lithium nitride, into your electrolyte and to increase the lithium ion concentration in the electrolyte system. Then, so during discharge, the lithium will go from the anode to cathode as a lithium ion. And then, so the sulfur on the cathode will be reduced into the lithium sulfide. And then during the charge, so then lithium ion will go back and here to be back as a lithium zero. And on the other side, so the sulfur will be oxidized. So lithium sulfide will come back here, oxidized to sulfur. And if we look into the charge and discharge voltage profile of the lithium-sulfur battery, so this is a typical discharge and charge voltage profile you can get. Because we start from the discharge, so we start from sulfur, and you will see, so at the discharge curve, we have 4 different stages. And at the first stage, you will have a first plateau. So this first plateau related to the reduce of sulfur into the lithium 2S8. So this is a polysulfides, lithium polysulfides. And then at the second stage, the long chains of lithium polysulfide will be reduced into relative short lithium polysulfides. And then in the third stage, we can again get a kind of plateau. So in this plateau, so this polysulfide, so this short chain polysulfides will be reduced to the lithium 2S2 or lithium sulfide. So these two are both already solid. So you will have a liquid to solid transition. And then in the last stage, so the lithium 2S2 will be further reduced to the lithium sulfides. So you will have a solid-solid reaction. So you can already imagine. So this is a rate determining state because the solid-solid conversion is very low kinetic. And as a summary, so when you combine all the reaction together, so we have at the anode, so lithium will be transferred to the lithium ion and to generate the electron here. And for the cathode, so it's sulfur. So sulfur here, it's always in the cathode, it will be S8. So sulfur is a kind of molecule. So you have a kind of ring structure with 8 sulfur atoms. So sulfur is not kind of different from others. So sulfur is always exist. So as a stable state, when you have a S8, so you always have a ring structure of sulfur. And so S8 will here get the electron and then be reduced into sulfide. And as a redox reaction here, so you have a reaction lithium with S8, then you get this. So this is like the total redox reaction. You combine the cathode and anode side. And here you will see, so this reaction is quite complicated because, so we start with sulfur 8. So sulfur 8 is a kind of solid material. Then during the discharge, you will form different kind of polysulfides. So first long chains and short chain polysulfides. And actually these are soluble in the electrolyte. So it's kind of solution. Then at the last stage of the discharge, you will again form the solid state of lithium sulfide and lithium 2S2. So you have a solid to liquid and again to solid transition. And the dissolution of the lithium sulfide in the electrolyte will give a lot of problem for the system because so it will move so from the cathode to the anode and lead to the shuttling effect. And this is called polysulfide shuttle effect. And in this case, so the sulfur, because polysulfide is soluble in the electrolyte, so it will go to the anode side. And this on one side will lead to the loss of the active mass because sulfur is the active material. If you go to the anode side, so you lose active material. And of course, because you lose this sulfur, so you will lead to the change of the morphology on the cathode side. And meanwhile, so you will lead to a passivation layer from the polysulfide on the lithium anode. This is also not good for the battery system. And moreover, so you will lead to the self-drain of the battery. And of course, yeah, you increase the charge time for the system. So that's why, so this polysulfide shuttling effect is a main problem for the lithium sulfur battery, which need to be avoided. The possible methods to inhibit or to suppress this shuttering effect. They are mainly based on 4 different methods if we look into the literature. So one is by adding the salts, so lithium nitride salts into the system. So in this case, it will make a kind of protect layer on the lithium anode and to prevent the passivation of lithium anode. And of course, yeah, you can use, instead of this liquid electrolyte, it's possible to use solid electrolyte. And in this case, of course, yeah, then the dissolution of polysulfide do not exist anymore in the system when you use the solid electrolyte. And another possibility is to optimize the conducting salt, and in this case also to improve the diffusion of lithium ion, and then to improve the polysulfide shuttering effect in the system. And the most favorable method, and these are also the main focus of the work on lithium sulfur battery, actually is laid on the design of sulfur host materials. And in this case, of course, you can more efficiently to suppress the polysulfide shuttering effect. So that's why, so in the next time, so we will mainly focus on the sulfur host material. So what kind of material we can use for the cathode for the lithium sulfur batteries. They are actually mainly based on 2 principles. So one is shown as the sham A here. So one is based on the physical confinement of the polysulfide. So in this case, you give a kind of physical barrier for your system. So when your polysulfide, yeah, so this is sulfur, then during discharge, you will form the polysulfide, and this physical barrier will give a kind of physical confinement to the system to avoid, yeah, this shuttering effect. But here, so we should think about, of course, yeah, so this physical confinement cannot reach 100% efficiency. So anyhow, you will have a kind of diffusion, yeah, of this polysulfide. The second possibility to improve the system and to solve this shuttering effect is to give a kind of chemical affinities, so have a strong affinity, yeah, of the polysulfides with the substrate. So then in this case, instead of kind of a physical barrier, you bring the chemical absorption or chemical confinement to of your sulfur host material with polysulfides. So you can form a kind of chemical interaction here. And due to this strong binding, of course, yeah, you can suppress diffusion or dissolution of polysulfides into the system. So this is a second approach for the design of the host material for sulfur cathode. And you can already compare, so of course, chemicals or this chemical absorption or chemical confinement normally is considered more efficient, yeah, but it depends the system. So the optimal system will be, of course, yeah, to combine both effects. So you have both the physical confinement with the chemical confinement of the polysulfides. And based on this, so we will look into the detail what kind of cathode material can be designed and synthesized. So first of all, based on the first strategy, so the physical confinement, this is mainly based on the carbon nanostructures. And you can see, so until now, really different kind of carbon structure has been synthesized and developed. So you can have either hollow or porous, and you have different morphology. So the physical confinement is mainly based on these porous carbon nanostructures. which can, of course, because carbon have a very good electroconductivity, so it can be used as the efficient sulfur host material for lithium sulfur battery. And on the other side, considering the chemical confinement, so then you need, of course, this special interaction between the polysulfide with your substrate or with your sulfur host. And here, of course, you have more possibilities. And I just give you 2 examples. So the first example is based on the nitrogen doped carbon. And due to this doping, so you will give a kind of interaction between the nitrogen doped carbon with the polysulfide. And you can see, so for this nitrogen doped carbon material, they have a huge increase of the absorptibility to the polysulfides. And as a second example, so this is based on the titanium metal-based, so this is titanium-based cathode material. And also due to the chemical bonding of titanium with the polysulfide, with sulfur, you can also lead to a strong chemical confinement of the polysulfides. And in this case, you can also use this as a kind of sulfur host material for lithium sulfur battery. But here you can see already, so for the chemical confinement, it's mainly based on the composition of your system. So it can be either carbon or metal-based compound. And some cases you can also using polymer as a chemical confinement for the lithium sulfur battery. So this we will talk later with different examples. And as a first example, so we first talk about these carbon materials, because carbon is one of the most often used and also the classical cathode for the lithium sulfur batteries. And so the Professor Linda Nazar, so she is one of the first one, so who developed this concept actually. So she's from Canada, and she is so her group is one of the best working on the lithium sulfur batteries, and she is the first one. And her first paper was published in 2010. So say using porous carbon as a cathode host material for sulfur. And in that case, they can see it can work efficiently. So for the lithium sulfur batteries. Actually, before her, people are also think about the concept of lithium sulfur due to the extremely high theoretical capacity value. Unfortunately, so the system does not work very efficiently due to the problem because you need a kind of sulfur host material, and the sulfur is isolated. How you can homogeneously embed your sulfur into your host. And so Professor Linda Nazar, so she's the first. So she gives a concept using porous carbon. And of course, in that case, the porous carbon have a very good catalytic, so have a very good conductivity. And also due to this porous structure, it can give the physical confinement. That's why, so she's the first get very promising performance for the lithium sulfur battery. And I just give you an overview here. So until now, different kind of carbon nanostructure has been synthesized on one side. So you see different morphology of carbon, like 0-dimensional carbon nanosphere, 1-dimensional carbon nanotubes, or 2-dimensional cis graphene. So layer structure, they can be all used as a host material for sulfur. And on the other side, so the porosity of the carbon, of course, can also play good role as a cathode. And you can combine the different porosity of carbon, for example, macroporous or mesoporous or even microporous host, depending on, of course, on the system. And I hope you still remember. So when we talk about the carbon material, we have discussed about the UPEC definition of this porosity. For the macroporous host, so it means a pore should larger than 50 nanometer. And for the mesoporous material, you have the pore in the range between 2 to 50 nanometers. And for the microporous system, you have the pore size smaller than 2 nanometers. So this is the system can be used. And I just want to mention, so for the Sulfur host, so the mesoporous system is more promising because when we think about sulfur, it's always exists not like single atom molecules. Yeah, you always has the S8. So if your pore is so small, so actually this 8 sulfur atom cannot go into your extremely small pores. So that's why the microporous carbon actually is not an optimized system as a cathode for sulfur. And I would so give you some example. Yeah. So what kind of research work has been done already based on the carbon materials? So first is the example is based on the porous carbon spheres. And in this case, the authors, they have used a kind of templating, so hot templating approach to synthesize the hollow carbon spheres. And they can really have a kind of architectural, so not only thin layer hollow carbon, but layer by layer. So it's a hollow in hollow carbon spheres. So we can look into the procedure, how they did this. So they using the silicon nanoparticle as a hard template, and they coated the silicon nanoparticle with RF. So RF is kind of resin from the rhizosignal and for formaldehyde. So this is a typical carbon precursor you can use. So they have a very good yield for the carbonization. Then they coat it again, yeah, with this RF resin with the silica, and upset they do the calcination. Then so RF, so the resin will be conformed into carbon, and then in the end, yeah, so silica can be etched, so you can remove the silica, and in the end you can have a kind of hollow, yeah, carbon spheres. And alternatively, they can also using a hollow in hollow carbon material. So in that case, so they repeat this procedure actually. So they coat it so on the silica, then they coat this RF resin again, then again a thin layer of silica. And then they do the calcination. Then you see they have a kind of a 2 layer of carbon with the silica between. Then in the end, yeah, they do the etching process to remove the silica and to produce such kind of hollow in hollow carbon spheres. And so this kind of particles, so you can also see clearly. So from the transmission electron microscopy. So from SEM, actually, you can see not so information from the SEM image. Yeah? You can see only a kind of sphere particle. But from the TM image here, you can see, so you can really see the different layer, yeah, of this carbon. So they do form a kind of hollow in hollow carbon material by these methods. Although it's very complicated, yeah, you can already imagine how many steps, yeah, you need. And of course, yeah, so the yield of your system will be extremely low, but does not matter. So it's a kind of proof of concept. And then they did the electrochemical performance. So for such kind of hollow in hollow carbon materials, and you can see here, so these cation materials, they show relative good, yeah, electrochemical performance. And this, they think, based on the effective physical confinement of this carbon for the polysulfides. Because normally, when you have only a kind of thin layer of carbon, of course, it can be worked as a physical confinement for polysulfide. But anyhow, you have always sulfur outside. Then on this side, you can always have the kind of dissolution of polysulfide in the system. However, you have like 2 layers of such kind of structure, you can really confine the polysulfides in your hollow structure. In that case, of course, you can improve this physical confinement ability in the system. So this is one example. So you can design your porous particle to improve the performance of lithium sulfur battery. So as a second example, this also they trying to make a kind of cathode based on graphene with carbon nanotubes. And they use a kind they called one-port self-assembly of the graphene carbon nanotube. The use of carbon nanotube is based on because carbon nanotube can form a kind of flexible and also freestanding material. Then in this case, you do not need to add any binder to make a kind of slurry. So you can use it directly as a cathode material for lithium sulfur battery. So this is advantage for this kind of system. And also they're using graphene oxide. And also, so the reduced graphene oxide, they have also very good conductivity. And it can be also used as a very good host material for the sulfur. And that's why they use a combination of graphene with carbon nanotubes. You can see already from the electrochemical performance here. So this is like a cycling stability test. They use 1C as the charge and discharge rate. So 1C means you need 1 hour to full charge and discharge your battery. So this is 1C. And you see, so they can have very stable capacity of their battery even after more than 400 cycles. And so they, of course, look into the morphology and they looks very good. And as a third example, so of course, carbon nanotube, as I mentioned, carbon nanotube, they can form a kind of sponge structure. So it's a very good candidate if you want to work on the freestanding cathode material without any binder. And also the carbon nanotube, because it's a fiber structure. So this is also a very good candidate if you want to make the flexible cathode material. And if you look into the literature, if you want to design some like wearable battery system or flexible battery system, most of them, they are based on the carbon nanotube or carbon fibers. So in this work, the author trying to modify the carbon nanotube because we know, so you can have like undoped carbon and they trying to use nitrogen to dope the carbon nanotube. And they even trying to oxidize the carbon nanotube. So they have 3 different kind of samples and they use this as a cathode for the lithium sulfur battery. And before they do the battery test, they also do the theoretic DFT calculation to calculate the binding energy between the carbon nanotube with the polysulfides. And here you can see, so this is undoped carbon nanotube. And they found, so for the nitrogen doped carbon nanotube, they show the high binding energy to polysulfide. And this high binding energy indicate the nitrogen doping of the carbon nanotube will give a higher or stronger affinity. So you will give additional chemical affinity to the polysulfides in this case. So then they do this electrochemical test for their battery system. You can see, so the green line is nitrogen doped carbon nanotube, red line is normal carbon nanotube, and blue line is oxidized carbon nanotube. And of course, so the oxidized carbon nanotube will show the worst performance because by oxidization, you will, of course, to lose the better electroconductivity of the carbon nanotube. That's why they show the worst performance. And for the nitrogen doped carbon, as they show already from the simulation, because you can give additional physical, so based on this physical confinement, but also additional chemical affinity, so the strong binding, yeah. That's why to the polysulfide, so that's why they show the better performance compared to that of not doped or non-doped carbon nanotubes. So our group have also worked on this topic, and based on this idea of carbon nanotubes, so we are also think about to use a kind of carbon monolith. And so for the carbon monolith, so you see the final product looks like this. So it's really like a black kind of pencil. So you can cut it with laser, then you will get a kind of piece, yeah, of this spherical piece of material. And this can be used directly as a cathode. And in this case, so it's also binder-free material. And this can be used as a model system if we want to do some operantal analysis, because then you do not have any disturbance from the additives in this case. And to synthesize such kind of carbon monoliths, we also start with RF. So this again, yeah, so we use this resorcinol together with formaldehyde. So this will be used as a carbon source. And then we add this diamide. This is using as a nitrogen dopant. So because if you want to have additional chemical confinement of the polysulfide, you need to do this nitrogen doping, as we see already from the work from other groups. And then we add this graphene, so reduced graphene oxide to increase the conductivity of the system. And the synthesis can be done very straightforward. So we do first the hydrothermal, so you use the autoclave and you do the hydrothermal synthesis, then you will get a kind of hybrid monolith. Then we do the calcination to transfer this RF resin to carbon. Then you will get such kind of carbon monolith. And from the SEM, you can see, so they have a kind of spherical structure for this carbon monolith. And for the nitrogen desorption and adsorption measurement, you can see they have a kind of porous structure. So you have a different pore, yeah, combined in such kind of carbon monolith. And of course, important, so we do the electrochemical performance, and they can be used as a kind of cathode for lithium sulfur batteries. But you can see here, anyhow, you still have this capacity fading, yeah, when we increase cycle numbers. And this is really due to because such kind of porous carbon, you cannot give 100% of the suppressing of this polysulfide shuttling effect. So that's why you always have a little bit of this fading. But for other example, we can show, so using metal-based compound, you can really have much better performance. So then another example, this is kind of hybrid material actually. So they're using the carbon nanotube. So they use a multi-wall carbon nanotube as a template. And then they trying to synthesize a tin oxide nanoparticle inside these carbon nanotubes and to form such kind of bamboo structure. And we know, so bamboo is a kind of very good structure for construction application due to the extremely high mechanical strength. This is like a nature structure which can give such kind of higher mechanical strength. So that's why the authors take this as a good example and trying to design their cathode material based on this structure. And then, so they do like this. So they take the carbon nanotube as a template. Then by this vacuum CVD, so they fill this carbon nanotube with tin atoms. And then by the plasmon reduction, so the tin will be ameliorate into the tin oxide, And as a final step, they use the melting diffusion process to add sulfur, so to load sulfur into the system. Then finally, they can have kind of sulfur loaded cathode. And this can be well see from this TM image here. So you see, so this is multiple carbon nanotubes. And then in the middle, you have this tin oxide nanoparticle. And of course, so from the elemental mapping, you can also well define where is the sulfur and where's the tin oxide and where's the carbon. So they can really synthesize such kind of structure as they designed. Then they do the electrochemical performance. And here I also show you the cycling stability test. And you see the blue curve here is the carbon nanotube with sulfur without tin oxide. And then the orange curve here is with the tin oxide. And the advantage here you see, so by adding tin oxide into the system, they show the better capacities, and also they show very good cycle stability. So even for 1,000 cycles for their cathode material, they explain like this, because if you do not have this tin oxide, so you have sulfur inside, and during discharge, you will have a kind of volume expansion due to this solid-solid conversion. And here you will have a kind of high volume expansion. And for the pure for the pure carbon nanotube, so this is not enough for such kind of volume expansion. But if you have the tin oxide between, then you can reduce such kind of structure deformation during discharge. So that's why during the discharge, such kind of bamboo structure can well defined for the lithium sulfur batteries. Instead of carbon nanomaterials, I also mentioned so polymer can be also a kind of host material for lithium sulfur batteries. And so, for example, the group of Yicui, so they are also one of the pioneer working on the lithium sulfur batteries, and they have kind of such kind of concept. So they use polymer to protect this sulfur and into a nanometer range. And then, of course, so during the discharge, the sulfur will be reduced to the polysulfide, and then further discharge will form a kind of a lithium sulfide here. So it can both, you have a hollow structure in between, so you will have a physical confinement of this polysulfide here, prevent from the shelter effect. So meanwhile, because you have a huge space in a hollow space in your particle, so it can also avoid this volume expansion during the discharge. And to synthesize such kind of hollow sulfur particle coated with polymer, they using PVP as a polymer layer, and they use a sodium thiosulfate as a precursor for sulfur, and this will be synthesized as the acid condition. And finally, you will get a kind of colloidal sulfur particle, which are coated by these PVP nanoparticles, which looks like this. You can see they do have such kind of hollow structure. And from the electrochemical performance, we can see, so they can work here as a cathode material for the lithium sulfur battery. And also, so although they still have some capacity fading, but anyhow they can work efficiently for long cycling. So they even tested for 1,000 cycles. And here I just want to mention, so here it's really a lot of work. If you think about one size cycle, you do like at 0.5 C. So you can imagine, so one cycle means you need at least 2 hours, depending on the sulfur loading amount. So this will be, so this one curve is already 1 or 2 months work. So because we need to wait for each cycle. And then, of course, yeah, they want to improve their system, because in this case, they use PVP, which is kind of amphiphilic polymer. And this PVP, actually, they do not have any kind of special affinity with polysulfide. So they can only give a kind of physical confinement here to the polysulfide. And then they think about if they can improve the system. And in this case, they want to coat it, this hollow sulfur particle, with a kind of conductive polymer. And conductive polymer, so here they do the DFT calculation, and to calculate the binding energy between the conductive polymer with the polysulfides. And they can show, so you do have the strong affinity with the conductive polymer with these polysulfides. And so in their study, so they use different, so 3 types of conductive polymer, like P dot, polypyrrole, and polyaniline. And so in all cases, you can see, so after the coating, they still form such kind of hollow particle structure. And you have a layer, very nice layer of conductive polymer can be seen here. And then they try to analyze electrochemical performance. And in this case, so depending on, of course, what kind of polymer they use, and they found, so for the P dot, so this is a red curve here, so the P dot system, they show the best chemical confinement with the polysulfide. And this is like also give a good concept here, so you can do the surface modification on your host material to give additional chemical confinement into the polysulfide shuttering effect. And as another example for these polymer systems, and so there are also some polymer, because sulfur, they can do polymerization. So sulfur is kind of, you can do the cross-linker with sulfur. So if you remember this natural rubber, if you want to cross-link it, you need to add sulfur and do this vulcanization. So sulfur is a kind of cross-linker. And so some researcher, they have thought about this concept, and they are really very smart, I should say. So they transfer this concept into the battery system. And in this case, they first synthesize a kind of conductive polymer. And for the conductive polymer, they have a kind side group. So this is a thiol group. And the thiol group can react with sulfur. And when you have a cross-linker, and you will have a kind of network based on this conductive polymer and the sulfur. So you do not need to load sulfur into the system. So the sulfur is already as a chemical binder or as a cross-linker. So it's already a part of your polymer chain. So you do have a chemical bonding of sulfur into your polymer matrix. And of course, so in this case, due to this chemical bonding of your sulfur with your polymer chains, you do not have any problem with the polysulfide, because you have one side, this chemical bonding, and you do not have this possibility for the dissolution of polysulfides. And they have proved by the electrochemical performance, and you can see, so the cross-linked conductive network with sulfur, they show really good cycle stability in the lithium sulfur batteries. And they also run for more than 1,000 cycles in this case, and at extremely high charge and discharge rate. So they use a 2C rate. So it means, so for one cycle, charge and discharge only need 30 minutes. So they can complete one cycle here. And so here I just want to mention, and so actually, so in Germany, we have now SPP, so they called Schwerpunkt program. So based on the polymer-based battery system, and Professor Uli Schubert, so he's from Jena, so Universität Jena. So he's the speaker for this polymer-based battery program. And so Professor Uli Schubert, he's also one of the best, so his group is one of the best in Germany and also in the world working on polymer-based batteries. And so in their program, so they also have combined the polymer-based lithium-sulfur battery in their program. As the last example for these polymer-based lithium-sulfur batteries, so as I mentioned already, so sulfur can have a chemical reaction, and so this group, they have also used this approach. So they trying to use sulfur and then have the chemical bonding of sulfur with their monomer. So they use dip. So this is have like two double bonds, and then you will have a kind of cross-linked structure, and with sulfur as a cross-linker. And so in this system, so they're using AAO as a template. Then they first use CVD method to synthesize the carbon nanotubes in the AAO template. And then they do this sulfurization of your system. So to fill, so this AO template, with this cross-linked sulfur polymer. Then, of course, you can remove the AO and other not reactant material. Finally, they got a kind of carbon nanotube combined with this polymer system. And then they use this as a cathode for lithium sulfur battery. So you can see, so they have really, so this is like the channel, looks like the channel from AO. So they can really copy the channel, from the AO. And this channel structure, so when we talk about the battery application, if you can synthesize such kind of like channel structure from theory, they believe so such kind of channel structure will be very favorable for the ion diffusion and transportation. So that's why this is also the idea behind why this group, they use such kind of AO as the template, so they can really promote the lithium transfer. And of course, so you see in this case, they do show very stable cycling stability for this polymer modified with sulfur as a cathode. And here they give the advantage for their system. On one side, so you have the carbon nanotube. So carbon nanotube, they can work as a physical confinement for sulfur. And then, of course, you have the carbon nanotube. So you can, like for this carbon nanotube, you can give additional space for this volume expansion during the discharge process. And of course, as I mentioned, so this conductive carbon tube, they can always give a very good path to fast electron transport. And for the polymer system, because we have a kind of this pipe electron structure of this polymer system, this will also enhance the lithium transfer, lithium ion transfer. And finally, because we have chemical bonding of sulfur with your polymer background and so so in this case you have a chemical carbon sulfur bonds, and this will of course very good inhibit the shuttle effect of the system. So as the last part, I would also discuss with you, so instead of carbon or polymer, so actually most of the attractive work on the cathode material is based on the metal compounds. And if we look into this here, you will see different kind of metal compounds can be used in lithium sulfur battery, and they actually play a multiplier role in lithium sulfur batteries. And the advantage for the metal compound is they can show much stronger absorption ability to polysulfide if we compare to that of carbon or conductive polymers. And as a metal, so you can be either metal sulfides or metal nitrides, and also of course, metal oxides is also a good example. And they also work with metal carbide or metal hydroxide. So really a different kind of metal-based compound can be used as a cathode. And we will mainly discuss about the metal oxide and also a few examples on metal sulfides and one example on metal nitrides. So you have a general idea how you can design the cathode material. So first on the metal oxide, and so the metal oxide, they are very attractive as a cathode for lithium sulfur battery because oxidation state of this oxygen, they always have a very strong polar surface. So this will give you a strong affinity with polysulfides. And so the researchers has already studied different absorption ability of metal oxide material to the polysulfides. And you can see here, so the vanadium oxide shows the best absorption ability compared to that of titanium dioxide and also better than this aluminum oxide. So there are really a lot of possible example based on these metal oxides. And so the vanadium oxide is the best absorption. And here, so the titanium suboxide, so we will talk about later. So they are very attractive because one disadvantage for metal oxide is they have relative low conductivity. But titanium suboxide, this is a kind of abnormal example because they have better conductivity. So that's why compared to other metal oxide material, they show very good electrochemical performance in lithium sulfur batteries. So as another example for metal sulfides, so in that case, so metal sulfides have also very good affinity, strong affinity to polysulfides. And here's also some example for the different metal sulfides material to their affinity, absorption ability to polysulfides. And here you see, so the titanium disulfides, they show the strongest absorption ability and better than that of cobalt sulfide. And I give you just some examples. So then why so different methods has been synthesized here. So one example is titanium suboxide. So this is titanium 407, and compared to that of titanium dioxide, you see, so you have one oxygen less. And this gives you actually, so you have one not centrated group on this phase. So you have a kind of high concentration of oxygen vacancies in your structure. And this oxygen vacancy will provide very strong affinity or very strong binding energy to the polysulfides. And on the other side, this oxygen vacancy will also bring the system with very high conductivity. So this is called this magnetic phase for titanium suboxide nanoparticles. And so this can be actually measured from the independent spectroscopy. You can see, so this black curve is titanium suboxide. And you see from this half spherical value, so this is a resistance. So you have the smallest resistance of the system. So it means they have the highest conductivity of the material. So, and also this also, they also study the chemical binding. So the binding energy of the titanium suboxide to that of the polysulfides, lithium polysulfides, and they also show very strong binding energy for these two materials. And of course, you can always easily measure this by the absorption test. So this is the solution of polysulfide. They always have a kind of red, yellow color. Then they mix this polysulfide solution with the titanium suboxide particles. Then they shake here. Then after a few hours, you see the titanium suboxide particles, they precipitate at the bottom. And meanwhile, the solution is colorless. So it means the polysulfides have been all absorbed onto your titanium suboxide. So this is a typical way we measure in our lab the absorption abilities. And you can, of course, when you have the color. So if you have the color, you can always measure by UV spectroscopy, then you can have a kind of quantitative measurement of this. So this also, so they use this kind of titanium suboxide as a cathode material, and you can see compared to, so this is only carbon, so compared to the pure carbon, the titanium suboxide, they show better capacity and also better cycling stability. And so this, they conclude, so on one side, so if you do not have any like chemical confinement, like if you have a kind of normal carbon material, so you do not have any special affinity with polysulfide, then in this case, of course, you can only have very weak absorptibility to polysulfides, and this physical confinement is not enough, so you always have a diffusion and then have the shuttering effect. And of course, so you can have a kind of a strong absorption. And in that case, you can have a polysulfide be confined into your substrate. However, if your substrate is like not conductive, like normal metal oxide, and in that case, you will have a very low sulfur utilization. And then the total system actually is still not optimized. However, if you can combine both, like on one side, the strong absorption ability to the polysulfide, so you can have suppress this shuttering effect. And on the other side, because you have a kind of conductive substrate, for this case is titanium suboxide, then of course you have a very high utilization of sulfur. So this all effects will give you a good promising results for the lithium sulfur batteries. Actually, we're also trying to synthesize the titanium suboxide in our group. So in our group, we're using the Broca polymer as a template. So we use a soft template method. And the Broca polymer we use is the styrene P2VP, and they can self-assembled into such kind of porous structure. And by the selective swelling, we can generate pores in the system. And then due to the special coordination of P2VP with the titanium precursor, so we can deposit the titanium dioxide first onto the porous particle. Then we do the calcination to generate this titanium suboxide in the system. And meanwhile, because we know the conductivity is also a very important issue for such kind of host material, so we're also trying to improve the conductivity by coating the system with a thin layer of carbon. So from the electron microscopy, so this is a TEM, you can see the porous structure made of the titanium suboxide. And we can also coat with a thin layer of carbon on it. And so they can make a very homogeneous slurry onto the current collector, and then we take this as cathode here. Then we assemble these coin cells. And by measure the electrochemical performance, so you can see the red line here. So this is titanium dioxide. You see after 50 cycles, the battery is dead. And then for the blue line here, so this is the titanium suboxide nanoparticle. They are quite stable, with high capacity until 300 cycles. And this performance can be even enhanced by the coating of carbon. So because it's in proof of the conductivity can also improve the performance of the lithium sulfur batteries. So then we will talk about this metal sulfide, because metal sulfide actually compared to metal oxide is more promising, I should say. This is because for the metal sulfide, compared to that of metal oxide, so normally they have better conductivity. And also meanwhile, they have the better affinity to the polysulfides. And if we look into literature, yeah, so nearly different kind of metal sulfides has been already tested as a cathode for lithium sulfur battery. So I just find some example for you. Yeah. So for example, so again, yeah, so this from Yi group. So he's from Stanford. So if we look into lithium sulfur battery, so he's one of the biggest guy, yeah, in this area. So in their group, they're using the silicon disulfide as well as this palladium disulfide as a cathode. And of course, yeah, so you can always using the DFT calculation to calculate the binding energy of such kind of metal oxide to that of lithium sulfides. And they show, so they have very good, yeah, strong binding. And by the electrochemical performance, so you see, so the both system, yeah, they show nearly similar performance and with very good, yeah, cycle stability. Molybdenum disulfide is also very promising system. And so these authors, they trying to also synthesize a kind of hierarchical molybdenum disulfide and to modify this with carbon. This is because so for the molybdenum disulfide, so compared to others, so their conductivity is still not so good. So that's why it's always nice if you can modify this molybdenum disulfide with a kind of carbon layer to improve the conductivity of the system. So as you can see from the synthesis schedule, so trying to synthesize, first, yeah, they synthesize this hierarchical carbon sphere as a template, then they immobilize molybdenum disulfide into this carbon sphere system, and in the end, yeah, so they're using the melting diffusion method to load sulfur into these particles. Then they use this as a cathode. Then from the electron microscopy here, so you can see clearly, yeah, so the carbon and so molybdenum disulfide is also a kind of two-dimensional layered structure. So you see clearly, so this layered structure of molybdenum disulfide. Then they first test the absorption test with lithium sulfide. You see, so this is a pure polysulfide solution. It's a dark yellow color. Then they mix with, so this is a carbon sphere. This is with the molybdenum disulfide. And you can see the strong effect, yeah. If you have this molybdenum disulfide in the system, then they can absorb these polysulfides immediately and lead to such kind of clear solution. And this, of course, yeah, you can also see from the electrochemical performance. So for this molybdenum disulfide modified carbon spheres, they show much better electrochemical capacity and also with better cycle stability. And so these authors, they have also trying to, so of course you can always open your battery coin cells, and to check what happens. And so the authors, they also open their cells, and you can see here, there's a kind of yellow color. So this means the sulfur, because sulfur is yellow, So this means you have already, so the sulfur to diffuse to outside. And this also a kind of indicate of the shuttering effect of the polysulfides. In the case of the molybdenum disulfide, you see the electrode is very clean. So this is also a kind of improvement. So the molybdenum disulfide, they have a strong affinity with polysulfide. And also another very important topic under discussion now. So people believe, so instead of this strong chemical confinement, there also a kind of electrochemical catalytic behavior from the molybdenum disulfide. And they believe so molybdenum disulfide can work as a catalyst for this redox reaction. So they can short the time for the generation of polysulfide. And this can, of course, to reduce the possibility of the dissolution of polysulfide. So this is also another possible reason for such kind of a metal sulfide system. So as one example for the metal nitrides, and so metal nitrides, so recently, so there are also studies working on these metal nitrides. However, compared to metal oxide and metal sulfides, one challenge is you can see also, so I show you the procedure, how to synthesize this. So this is titanium nitride. So this group here, they do the similar. So they first synthesize the titanium dioxide. Then you need to do this nitronization. And for this treatment, you need to treat your particle at extremely high temperature under ammonium gas. And so you know this ammonium gas is very toxic. So for such kind of treatment, you need a special device and also a very good safety issue consideration of the lab. So that's why, so actually not so many groups can do such kind of reaction. And this is also the reason why compared to other metal oxide or metal sulfide, so the metal nitride particle are relative less, not so many study has been done on it. However, so this group, yes, they have managed to synthesize such kind of titanium nitride particles. And then they also, again, use this melting diffusion methods to load sulfur into their hollow particles. So you can see from the TM image here, so the sulfur can be really loaded into the titanium nitride hollow particle. And the formation of titanium nitride can be also well proved by the XRD measurement. So they see, so this is a precursor. Then they first form the titanium dioxide in the form of anatase in this case. Then finally they form the titanium nitride. And from the electrochemical performance, you can see clearly, so the metal nitride system show much better performance than that of this red line, so this titanium dioxide. So this is because the nitride system, they have much higher affinity to the polysulfides compared to that of oxides. So as a summary for the lecture today, so as I mentioned, so considering the cathode material for the lithium sulfur battery, so of course there are two strategies in the moment. One is the physical confinement, and concerning the physical confinement, of course, we should pay attention onto the structure design of such kind of cathode material, which are mainly based on carbon. And in that case, of course, we can design really different kind of structures and to have a kind of a hierarchical structure to work as a cathode for lithium sulfur battery. And compared to this physical confinement, chemical confinement is, of course, much more attractive, because in this case, you can really improve to suppress the polysulfide dissolution in the system. And for the concept of this chemical confinement, of course, so you can always considering the inorganic compounds, what you can use here for the cathode. So you can use like metal sulfide or metal oxide, or you can use the conductive polymer, or you can use like a nitrogen doped carbon. So it depends on what kind of inorganic metal you can use. And on the other side, so this organosulfur, so you can always use sulfur to have a chemical bond, so to form such kind of carbon sulfur chemical bonding in your system. And in that case, this chemical bonding of sulfur into your polymer system will, of course, have a very good affinity to polysulfides, and then in that case can be improve the electrochemical performance. So this is the main strategy we can use for the design of the cathode material. And so with this, so So I have gone through all of our slides today. And so is there any question from your side? So I do not hear there's any question. And so on next Tuesday, we will have our last lecture. And unfortunately, so normally for the last lecture, I always organize a lab tour in my lab here at HZB, so in Wannsee. But unfortunately, so this year, due to this corona things, we cannot organize such kind of lab tours. But so my Humboldt fellow, Dr. Yaolin Xu, so he will give in short introduction on this battery system beyond lithium. So we will have a short talk from him. And then after that, we will discuss about the details about our examination. And because I think you also received the mail from the university, and for this online examination, so I think I can also ask you here. So I need the confirmation from all of you, because if some of you would like to prefer this face-to-face examination, then we should do face-to-face. And I need like a kind of agreement here from you.
Do you need that agreement to be in written form?
Yes. So it will be nice because, but anyhow, you will send me your topic for your short talk for your presentation. So maybe when you send me the title of your presentation, you can also send me a kind of confirmation, like you agree, this online form for your final exam. But so if some of you prefer face-to-face exam, then we should organize it. So that's why I want to ask you now. So if you want to have.
Excuse me, Professor, what do you mean face-to-face exam?
Then we need to meet together in one lecture, in one lecture room.
But the final examination is like a presentation, right?
Yes. So because this a kind of we need a kind of agreement, because this is not, how to say, this is not normal exam form for the university. This is only due to this corona situation, so we are allowed to do this online exam. Otherwise, we always need to meet, so like face-to-face, I mean, not by this online method.
Okay, so if we write you an email with our like matriculation number and our topic, would be enough for you?
So no, so for this email, so that's why I also need one additional sentence from you that you would like to have this online exam.
Okay,
form.
okay, thank you.
Instead of face-to-face.
Okay, thank you.
Yeah, because otherwise we need to organize a big lecture room, in the university. Then we do, in a big lecture room. Yeah, great.
And when do you need this mail?
So you can send me, so when you decide your topic, for your presentation. I do not need it like now. Before our exam, then it's fine. But I can also send you a mail, to this point, what I need, So I need the title of your presentation, and then I need so this confirmation from you. You agree, this online form for our exam, and then I also need this number, so your registration number, at the university. And also, of course, from which university? Because we also have the student from this Berlin polymer science program. Because in that case, I think you are not from University of Boston. Then please also give me like at which university you have been registered. Good. So these are all the information I would like to discuss with you today. And then we will meet here on next Tuesday again for our last lecture.
Professor,
then,
could I have 5 minutes of your time to chat?
Yeah, of course,
Thank you.
Yeah. So then the others have nice evening. Yeah. Bye.
Thank you. Bye.
Thank you. Goodbye.
Bye.
Bye.
Can you hear me?